Welcome back to the module 3 of the course Ultrafast Optics and Spectroscopy. In this module, we are studying different nonlinear effects which can be generated due to propagation of ultrafast pulse through a dielectric medium. We know that ultrafast pulse is a propagating electromagnetic wave. Propagation of an ultrafast optical pulse in an optical medium, particularly in a dielectric medium, results in many nonlinear effects. We have already seen that at high electric field strength, when radiation field is comparable to the atomic field strength which binds nuclei and electrons, the relation between the polarization and the input radiation field no longer remains a linear one. The general relationship between the polarization and the input electric field is then expressed by Taylor series expansion, which is given here. This polarization and these are the input field, and it depends on these powers. The terms proportional to E square, E cube, and E to the power 4 and so on represent the nonlinear polarization of second, third and fourth order respectively, and this chi, associated chi, they represent frequency dependent second, third and fourth order electric susceptibilities respectively. We have seen that each polarization results in several outcomes. So what happens, we will draw this figure which we are familiar with now. This input beam entering the medium, this input beam will say EIN, and this input beam is changing the polarity all the time in every half cycle, and this is why we are creating a dipole in the dielectric medium. A dielectric medium is a medium where there is no free electron, just like metal. It has an ion core, and then surrounding we have electrons bound to that core. Similarly, here I have an ion core and then electrons bound to this ion core. There is no free electron or the electron which can move freely in the medium. So what happens when we the input, due to the input electric field, we distort this electronic cloud. We distort it like this way. Let's say we distort it like this way. This is positive, this is negative. Again, but this distortion is not static distortion. This distortion is dynamical distortion because it's changing over the time. And it's changing over the time because the field, electric field, is changing the direction in every half cycle. And that's why this distortion will also change the polarity in every half cycle. So I will get different, at different time I will have these changes. This is as a function of time. So what is going on in the end, dielectric medium is behaving like an oscillatory dipole, and any oscillatory dipole will create new radiation, and that is the emitted radiation which we see. So this oscillatory dipole will oscillate. This dipole will oscillate, and due to this oscillation I will create a new beam that is called emitted beam, and this emitted beam is due to this emission occurs due to this dipole oscillation. This is a E emitted. So these are the three-step mechanism we have been discussing in this module, and we represent the nonlinear effect, nonlinear frequency generation with the help of this figure. Now we said that if this oscillation of the polarization, this oscillation of the dipole is due to the is manifested in the medium by the new polarization, time dependent polarization, which will depend on the power which will controlled by the power law. And let's say I have second order process, so in that case I can write down polarization as chi 2 E square. This is within bracket, we are saying it's an order, and without bracket it is this is a power, so E square. So this is input beam. So if I express input beam in a following way, E naught e to the power I omega naught t, let's say I have monochromatic plane wave. The same is true for the pulse as well, but if I have monochromatic plane wave, then I have this this one, and then pt equals, I can write down E naught square e to the power 2 I omega naught t. So what does it mean? It means that the polarization which I will create due to propagation of this input beam, the second order polarization which I will create, which will also oscillate at 2 omega naught frequency. So omega naught is the angular frequency for the input beam, and the polarization which I have created will have a oscillation with 2 omega naught frequency. And we know that what is the frequency of the dipole oscillation, that's the same frequency we get for the emitted beam. So E emitted will have similar characteristics of E square e to the power I 2 omega naught t. There will be a phase matching condition which needs to be fulfilled as well, but from a simplified point of view, we create a new frequency which will oscillate at 2 omega naught. That's why if we use 800 nanometer as input beam, we get an output beam 400 nanometer. So this is all about frequency conversion. We can have different outcomes, and we have seen many outcomes. Here in this in today's talk, in today's lecture, we will be focusing only on the third order process and higher order processes. So these are the processes which we are interested in this lecture. First, we will consider third order process with two beams in non-collinear configuration. Non-collinear and collinear configuration, we have seen it already. We have a medium, the nonlinear medium. This is nonlinear medium. In this medium, we can have a beam propagating along this direction. If the beam is propagating along this direction, then if it is SHG medium, second harmonic generation medium, then I will have the parent beam going, but let's say 10% of this parent beam will be converted to the second harmonic beam, and second harmonic beam I am representing, and they are propagating collinearly with the input beam. So this is the SHG beam, and this red one is the parent beam. This is the input beam, or sometimes we call it fundamental beam. So this is collinear configuration. In non-collinear configuration, when you think of it, we have, let's say, two beam non-collinear configuration. I have one beam coming like this way, another beam coming like this way. They are interacting in the medium, nonlinear medium, and due to this interaction we can have some frequency generation, and we have seen that some frequency generation can be shown like this way. This way we create some frequency generation, SHG, the SFG, some frequency generation, SFG. So this is non-collinear configuration. We'll assume that we have non-collinear configuration, and if we have non-collinear configuration, then each beam will draw this non-collinear configuration one more time here to show the fields. So I have this medium and this one input beam going like this way, another input beam going like this way, and I can write down these input beams as the complex notation is going to be E1, and this is going to be E2, which is nothing. E1 can be written as, if it is the real field, I can write down as half of A1 t, that is the envelope function, e to the power I omega 1t minus k1z. This is plus I have a1 star t e to the power minus I omega 1t minus k1z. So this is the way we represent the real field in the this is the real field of the first beam, and similarly real field of the second beam can be written as half of this a2t plus a2t e to the power I omega 2t minus k2z plus a2 star t e to the power minus I omega 2t minus k2z. So this complex conjugate is nothing but Euler principle, which suggests that cos theta equals half of e to the power I theta plus e to the power minus I theta. So this is exactly what we are. Cos theta is the representing the real field. So what we have given is the at this point where two beams are interacting in non-collinear configuration, at this point this electric field at this point is represent total electric field. Electric fields are additive, so total electric fields is going to be of this kind. Now if I consider medium's third order nonlinear response, which means that I will consider only third order process, which is nothing but epsilon naught chi 3, that's the third order susceptibility, multiplied by E input beam to the power cube. And if it is so, then I can express approximately third order process as the cube of this full the total electric field. And if I cube it, then I can consider this term to be A, this term to be B, this term to be C, and this term to be D. This equation is reduced to 12 standard equation or 10 standard equation of A plus B plus C plus D whole cube, which can give many terms. And we know each term is interesting and gives rise to certain nonlinear effect. We have seen that before. Now we will quickly go over each one and then come back to the term which we are interested in this lecture. Now if we look at the a cube term, let's say I am interested in a cube term. If I am interested in a cube term, is nothing but then a1, this is a cube term, a cube which is equivalent to a1 cube, a1 cube t into e to the power I, then 3 omega 1 t minus k 3k 1 z plus a1 cube star t e to the power minus I. This is a cube term. So a cube term is going to be only this part. So what does it suggest? It suggests that if I have a cube term, if I consider a cube term, then the polarization will depend on this this oscillatory function. This induces polarization, and this gives you the third harmonic generation, a new emitted pulse centered at 3 omega 1 along the direction of the k1. So 3 k1 suggesting that I am following still k1 direction, and 3 omega 1 suggesting that the new frequency which will be generated is at 3 omega 1. So what does it mean? It means that when I have non-collinear configuration and I have this, when I have non-collinear configuration and I have two beams going like this way, each direction, this is your k1 direction, this is your k2 direction. So this cube, a cube term will produce third harmonics along the same direction. So along that direction I will produce another beam which is going to be this one. This is going to be 3 omega 1, and this is going to be another beam. This is going to be 3 omega 2. Along the input beam we are going to create this third harmonics. The polarization associated with this a square c term, we can take a look at it, and the polarization can be can be written in a following way. We can write down the polarization of with the term a square c. So a square c will give me a1t square e to the power I omega 2 omega 1 t minus 2 k1 z multiplied by c. C is this one, so a2t e to the power I omega 2t minus k2 z. So if I simplify this, I get a1 square a2 e to the power I, then 2 omega 1 plus omega 2 minus I have t, and then minus I have 2 k1 plus k2 z. This is the term we get. So polarization, this polarization will induce another beam. It will produce another beam at 2 omega 1 plus omega 2 frequency, 2 omega 1 plus omega 2 frequency in this frequency. But which direction? Direction is going to be 2k1 plus k2 direction. So this is the direction I have to follow, and 2k1 plus k2 direction is shown it here. It is not along the perpendicular axis, which is shown through this gray line, is not along that axis, it is off the axis, but the direction is shown here 2k1 plus k2. This is called sum frequency generation, third order sum frequency generation. Sum frequency generation can happen in second order as well as third order or higher order. It's just it's combining them. On the other hand, I can have difference frequency generation, which is shown it here. Difference frequency generation is due to a square d term. We can take a look at a square d term as well. In a square d term, we have a1 square e to the power I 2 omega 1 minus 2 k1z multiplied by a 2 star, because it's a d, so this one is d, so a 2 star e to the power minus I omega 2t minus k2z. So if we simplify it, then what I get is that a1 square a2 star multiplied by e to the power I 2 omega 1 minus omega 2 t minus 2 k1 minus k2 z. So what I get is that difference frequency generation, this polarization will create a new beam at 2 omega 1 minus omega 2 frequency, and the direction is going to be along this 2k1 minus k2 direction, 2k1 minus k2 direction, which is shown it here. So if we project that, so let's say I have a nonlinear medium and I'm seeing it from the top. So I have two beams going along this way. These are the two beams, input beams. So on a screen I will have one spot here, one spot here due to the input beam. Now in addition to that, I will have one more spot here at the same position these are the third harmonic generation. Then I will have, if this is the perpendicular axis, then I will have one more blue spot, which is a new beam created at this point, that is called some frequency generation 2 omega 1 plus omega 2. So this blue part is 3 omega 1 and this blue is 3 omega 2. So I'll have two beams here and here, that both is going to be 2 omega 1 plus omega 2. On the other hand, here we'll have one more beam and here we'll have one more beam. This beam is difference frequency generation 2 omega 1 minus omega 2. This is called difference frequency generation. So both difference frequency generation. So looking at the position on a screen, we'll be able to identify each beam on the screen, and one can identify where is the difference frequency generation occurred and where the some frequency generation occurred. Now, in the end, the last term which we are interested in here is this term, this ACD term, and we quickly went over this term in our previous lectures. ACD term is nothing but two beam coupling. ACD term, I'll write down the expression associated with ACD, and that will clarify immediately why it is two beam coupling. ACD is an interesting two beam coupling term. Now ACD can be written as A1T, this is ACD, so A1T, and then C is going to be A2T, and then D is going to be A2 star T, then e to the power I can write down e to the power I omega 1 t minus k1 z multiplied by C is A2, A2 is already written, so multiplied by e to the power I omega 2t minus k2 z multiplied by e to the power I plus I omega 2t minus omega 2t and minus k2 z. So this is your A term, this is C term, and this is D term. If I multiply, then what we get finally, if we simplify this one, then we get A1t, then A2t square modulus, and then e to the power I omega 1t minus k1z. These two terms cancels out, and we get finally this this expression. So what does it mean? It means that I will get one more beam which will be propagating along k1 direction, but that beam, see, A1t e to the power I omega 1t minus k1z is representing the first beam, this beam, because this input beam was nothing but A1t e to the power I omega 1t minus k1z. So the same beam I get back, but it is getting affected by the intensity of the, this is expressing the intensity of the second beam. So the first beam I'm getting back here with the same frequency, but its amplitude or its overall shape is getting affected by the second beam intensity, and that's why it is called two beam coupling. An implementation of this technique is called polarization gating. So we'll go over the polarization gating in details. The third order polarization term, which is responsible for two beam coupling, is expressed as we have seen that it can be expressed as, that is associated with ACD term, third order polarization, which is responsible for this polarization grating, is AT, then A2T, that is the intensities, multiplied by e to the power I omega 1t minus k1z. This is the term which is responsible. This third order polarization yields emitted pulse that has the same frequency and direction as the first beam, but allows the first beam to get affected by the intensity of the second beam. So the first beam is getting affected by the intensity of the second beam. That's the basic idea of this term. Polarization getting involves two input beam propagating in non-collinear geometry. One beam's polarization is rotated at 45 degree to the other. So what we are doing here is that that's the configuration we take, because both beams, so the beam which is, we said that polarization in the two beam coupling, we are seeing, we have said that the new beam which is created is going to be traveling along the same direction of the input beam, this K1 input direction. So it's very hard to differentiate or separate these two beams, the output beam which has been created, the emitted beam which has been created by this polarization, and the corresponding input beam. Because they are propagating along the same direction, it's very difficult to separate them. So we have to use some optical trick to separate them. The optical trick is that the first beam we have taken to be vertically polarized. This sign indicates that it is vertically polarized. Vertically polarized, what does it mean? Let's say this is the direction of the propagation direction. Along this propagation direction, this is the vertically polarized beam, and this is horizontally polarized beam. So the vertically polarized beam, it means that it is it's the arrow, the electric field, locus of the electric field is pointing towards us if we are looking at the picture from the top. And on the other hand, the other beam, the second beam we have taken, the second beam polarization has been rotated at 45 degree, which is shown here by this green color arrow, double-headed arrow. So 45 degree, the moment we rotate it at 45 degree, then I can have a components along the y and z direction. So what we have is that the first beam is vertically polarized and relatively low intensity as well. This has low intensity. So this beam doesn't induce nonlinear polarization in the medium itself. However, the polarization of the second beam is rotated at 45 degree with respect to the first beam. So if the first beam is vertically polarized like this, then second beam is going to be rotated at 45 degree. So polarization looks like this. This is the second beam and this is the first beam. Furthermore, second beam is intense enough to induce nonlinear third order response, which will affect the weak field of the first beam. That's the way we would expect. So this is intense enough and this is low intensity. Now the weak field can be decomposed into orthogonal field components so that one stays parallel to and another stays perpendicular to the strong field. So this one is the strong field. I will change the color. The strong field color will make it, as shown here, will make it green. So this is the strong field, intense field, second beam, and the weak field is shown by this red color, and both the polarizations are different. They are rotated by 45 degree. Now what will happen if I have this situation? Then I can decompose my first beam along this direction as well as perpendicular to that direction. So I can have two different components for the weak beam. The one component would be parallel to the intense beam, strong field. Another one would be perpendicular to that to the strong field. Strong field, when we induce a strong field in the medium, it induces optical Kerr effect. We know optical Kerr effect right now. We know that nonlinear refractive index depends on its intensity such as and following this equation. So, this is a nonlinear refractive index. So, what happens when we use a when you use a field, a strong field at this at the 45 degree angle, we create a big nonlinearity along this line, along this direction, and that depends on the intensity, because intensity is very high. But along this direction perpendicular to it, we have we do not induce that effect, because it depends on the intensity. Intensity is localized along this direction only, but because intensity is not localized along this direction, we do not create appreciable Kerr effect or nonlinear refractive index. So, what happens, the medium, in the medium, this is going on in the medium. In the medium, we see that along a particular direction I have high intensity, and this high intensity is giving higher nonlinear refractive index. So, along this direction the medium is giving different refractive index as compared to this direction, this perpendicular direction. And because of that difference, the medium can behave like an anisotropic medium. It's not and it can show nonlinear birefringence. This means that nonlinear refractive index seen by weak field component parallel to the strong field is different from that seen by the weak field component perpendicular to the strong field. This nonlinear birefringence experienced by weak field components leads to polarization rotation of the weak field. This weak field, when it's propagating through this, due to this nonlinear birefringence created by the second beam N2I plus N0, this is the nonlinear refractive index, this beam polarization, this input beam polarization will be rotated. Thus, medium acts as wave plate. Wave plate, we know that wave plate can rotate the polarization. So, medium acts like a wave plate when these two pulses are interacting with each other, and due to the strong field created in the medium by the second beam. And with sufficient intensity of the second beam and with an optimum medium length, a full 90-degree rotation of the polarization of the first beam can occur. So, what we are showing is that after propagation through the medium, I have both vertical polarization given by this circle and horizontal polarization given by this double-headed arrow. Both are there. So, vertical polarization representing the input beam. Input beam, it is not possible that 100% of the input beam will be converted in a nonlinear conversion process. It is just fraction of that input beam will be converted. So, fraction of the input beam polarization has been rotated by 90 degree, and most of the beam still vertically polarized. But now we have two different polarizations. One is horizontal polarized light, that is the beam which we have created due to this polarization getting. On the other hand, the vertical polarization is remaining to be the input beam polarization. Thus, final emitted beam and the weak field, although they are propagating along the same direction, have orthogonal polarization. They can now be separated by a polarizing beam splitter. So, this kind of beam splitter is available which can separate two polarizations in along two different directions. This arrangement is called polarization gating, which is used in polarization spectroscopy or polarization gating spectroscopy, and is used in nonlinear optical spectroscopy and nonlinear pulse measurement. Phenomenological interpretation can be easily given here. Birefringence can only be seen in anisotropic medium, that we know already. However, transient anisotropy can be introduced in the medium by utilizing strong field. Strong field here we have used for the second beam. Here electrons oscillate along with the incident field at 45 degree, but due to high intensity, the electron cloud in the medium gets distorted, which introduces transient anisotropy in the medium. Then the medium transiently acts like wave plate, optical device which is used to rotate the polarization and rotates polarization of the first beam. So, the medium, this medium behaves like an wave plate at a particular intensity of the second beam, and that is why it can rotate part of this input beam, first beam to, by 90 degree, and we can now separate it. And this rotation is possible only when they are spatially and temporally overlapped. If they are not overlapped, this transient anisotropy cannot be realized. So, this is a beautiful demonstration of the ACD term which we have already shown. This is two beam coupling. We will stop here and we will continue this module in the next lecture.